So, here we go again. Welcome back. Good to see you. Happy Friday Eve. Just about there. You want to leave it open or no?
Well, I'm just wondering because if it bothers
you
you,
want.
just tell me.
Doesn't matter to me.
It's kind of wonderful.
Just a little bit. Graded homework. Due tomorrow, right? Make sure you're working on that. And then test is going to be Wednesday. So we'll do a lesson today, lesson Monday, and then Wednesday's the test. Okay? Please make sure you're looking at the test review. That will help you out quite greatly. And remember, it's a 2-day test. You'll have part 1 and part 2, but you won't be able to revisit a part. So once part 1's turned in, you're done. Then you do part 2 the next day. Okay? So today, it's not a bad lesson. It's actually something that we know already. It's just kind of reviewing it and just reviewing it with notation. It is 2.4 linear equations in 2 variables in linear functions. Okay? So our objectives, we're going to graph linear equations in 2 variables. We're going to determine the slope of a line, apply slope-intercept form, compute average rate of change. That won't be like new, but notation-wise we'll talk about more. And then solve equations and inequalities graphically. Okay? This and 2.5 kind of go together nicely. So this is like part of the idea and concept, and the 2.5 will finish it for us. You don't need to copy down the scatter plot. But looking at that scatter plot, this is, anyone golfing here? Any golfers? Okay. I was gonna say, yeah, you've been gone for golfing, yeah. I golf, it's a lot of fun. I was a soccer player for like 10 years and then I switched to golfing. Didn't want to, I mean, I wanted to golf, but the soccer coach was awful. And I was like, I ain't gonna play for you anymore. That's a different story. So this is a club head speed versus distance. Okay, so the x values are all the speeds of the club, and then this is the distances that come out of it. And if you notice, okay, I cannot connect all those data points with a line, right? There's no way I could do that. That's why it's called a scatter plot. But what I can do is I can estimate a line that's kind of close to this as possible, right? Like that kind of represents the majority of the data set. If you take a statistics class, which I would recommend, statistics is a great like application type math course, you will actually create a line mathematically that minimizes the distance between all those points to where it's a more accurate reading, okay? But looking at it though, this is a linear function, right? What we graphed here. And because we have a linear function, okay, we can find the slope of it, interpret the meaning of it, okay? We can find an average rate of change with it. So some of these concepts we're going to talk about in this lesson, we can kind of relate back to the scatter plot there. But figured, it's kind of cool just to see one of those. All right, so here we go. So going off the scatter plot here, the graph represents a scatter plot. It's a visual representation of a set of points. The line that models the set of data is called a regression line. The line shown in the graph was created by 2 points. Therefore, it's not a regression line. If you remember from Algebra 2, we did something like this where we picked 2 points that best represent the line. So that was our like line of best fit. A regression line doesn't do that. A regression line uses every data point to create the best line possible for it, okay? So just to make a comparison, a regression line takes into account all data points and finds a line that minimizes the distance each point is from the observed can't write today observed data value and the predicted one. We call the difference a residual. Okay, so again, our regression line takes into account all the data points, and you find a line that minimizes the distance to this guy, okay? So that's the objective, and again, this is my hand-drawn graph here, so kind of hard to model it, but that's what I'm trying to do. All these little distances here, I want to minimize it as much as possible. That's what a regression line does, okay? Now, the difference, we call these residuals. So we're trying to make the residual for all of these guys as small as possible, okay? In statistics, you talk about different ways of how to do that. And then you start using different graphing tools and programs. When I was doing my master's degree, it was called R. It's actually a free program. I think it's just the word R. R lab or R, but it's just R, and we did all of our calculations with that. It was pretty cool. So you're able to create regression lines and do different statistical tests with it. Okay, so this stuff here, just make sure you know what those terms mean. Okay, we're going to do a lot with regression here, not necessarily. Okay, might show up in a future project. Maybe I might have you guys explore it a little bit more, but for right now, this is just like a little bit of information about it, so that way you're good to go with it. Okay, so here we go. Definition. Let A, B, and C represent real numbers such that A and B are not both 0. A linear equation in variables x and y is an equation that can be written in the form ax plus by equals c. Okay? So looking at that, we've seen that before, and we had a name for this, okay, if you recall. So this right here, I'll put beneath it. So this is called the standard form of the equation of a line. Okay, so that's standard form. And standard form, it has some benefits, has some uses. It allows us to graph intercepts pretty quickly because you can just plug zeros in. So not always the most efficient in terms of some cases, but it can be. Let's try an example. We're going to graph the line represented by each equation. Okay? So let's look at, we got 3 examples here. So part A, part B, and part C. Okay? So in your notes, if you'd like, you can, that's a weird equal sign. you can go ahead and just draw like a nice little coordinate grid underneath it, just something that you can start plotting points with. Okay. So I'll do that as well. Okay. Just something like that. Nothing too fancy. So for the first graph, okay, notice that it is written in a standard form, okay? You could divide everything by 4 first, make it smaller, make it easier to graph, but it doesn't matter. I think it's easier if we switch this to slope-intercept form. So if I solve this for y, I get 8y equals negative 4x plus 16, and then we'll divide by 8. So that gives me a negative half x plus 2. Now that it's written that way, I can see the y-intercept quickly. So the y-intercept's going to be 2, and then the slope's negative a half, so down 1 to the right 2. And, I mean, 2 points is good. If you want to get really accurate, you can plot more. So, I don't know, go down 1 over 2. You can plot 1 more if you want. And there's my graph. Okay. Which, again, nothing too groundbreaking. We've done that many times in your many years of mathematics in high school and middle school. Okay, over here, we'll just get y by itself again, so this would be y equals 8. Now, notice that there's no x's, right? There's no input. So x could be any number whatsoever, just the output's always going to be 8, right? Okay, so that means it must be 1, 2, 3, 4, 5, 6, 7, 8. It must just be a horizontal line. Wow, I really missed the mark there. Let's try that again. Still missed the mark. Okay, we're just going to make a big dot to minimize the difference there. So yeah, no matter what x value I choose here, okay, the output's always going to be 8. And then over here, it's kind of the reverse. There's no y values, okay, but every x value that's a 4 is going to be paired up with every y value that exists. So this is just going to be a nice, yep, missed it again, nice vertical line here. So again, y can be any value, but they're always being paired up with 4. Okay? All right, let's keep moving. So the slope of a line passing through distinct points x, y, and we'll put 1s there. Just indicates point 1, and x2, y2 is the following. Okay, so just defining what slope is, right? And we're going to need this when we talk about average rate of change. So we're just kind of refreshing our minds with this. So delta y over delta x. Delta y, that's what the triangle is, that Greek symbol, that triangle means delta, just means change. The change in the y values, and this means the change in the x values here. All right? Provided, this is important, that x2 and x1, when you subtract it, you don't get 0. Because if that's the case, well, you don't have a slope anymore. It's pretty much undefined for us. So let's put an example to it. So find the slope of the line passing through the given points. And our points are going to be a half and a fourth, and an eighth with a 16th. Now again, nothing groundbreaking, you know how to find slope. But what I want you to do is, as we're going through these examples, think about what slope means, like the interpretation of it. It's the change of values, okay? That's the thing you want to really cement in your brain. It's the changes of your y, the changes in the vertical direction over the changes in the horizontal direction, okay? So here we go. Doesn't matter what your first or second point is. We'll let this be the first, this will be the second. So we're gonna subtract the y's up top, so that'd be 1/16 minus a fourth. On the bottom, we have 1/8 minus the half. Okay. So common denominators, which really isn't that bad. So looking at this, we have, that'd be a 4, so that's 16. That'd be a 4 up top, so 1 minus 4 would just be a -3 over 16. Okay, in the bottom, common denominator would be 8. So multiply this by 4, so that's an 8. That's a 4. So 1 minus 4 would be another -3 over 8. Now, one of those things where if you need the extra step of what this looks like, okay, you're just multiplying by the reciprocal. You're dividing a, almost fell. Dividing a fraction by a fraction. We can see that the -3's are pretty much going to be gone along with the negatives. So my final answer would be 8 over 16, which would be, not a 12, be a half. Where did that 1 come from? Half. Okay. So, nothing bad there, right? So again, what's changing? So the x's are changing by, a difference of 1, the y's are changing by differences of 2 there. Okay, let's talk about some graphs. So I'm gonna go back over here. So we're gonna find the slope. That's not too bad. Yeah, just do that. I feel like as the year progresses, I get better at drawing like lines nice and straight and stuff like that. I think I'm just still at the beginning where my hands are not quite used to writing from the board yet. So, it'll improve. We got a lot of graphing in the future with rational functions, so it better improve. So we got to find the slope of these two guys. So looking at A, and put it this way, these are slopes, like this is just your normal slope type of question. These two questions here are trying to show you some special cases with slope. So for part A, if you notice, it's not rising at all, right? No rise whatsoever. But there is a horizontal change. So if you're looking at your slope formula, well, up top it's just going to be a 0, right? And on the bottom it's just, well, it'll be a number, but it won't matter. So for this guy, okay, slope is just 0. Okay, that's it. Now, I put 2 points up there. If you still don't, like if you're looking at yourself like, I think it's 0, but I'm not sure, I mean, you could plug points in. So if you look at this, it'd be 6 minus 6 over 4 minus 1, which is 0 over 3, which is still 0. So again, if you're not sure of the special cases, just pick 2 points. Make sure that it is 0. Okay, and then for part B, kind of the same thing. That's a vertical line. It's rising a lot, but not any sort of horizontal change. So that means that the 0 is in the denominator, which we know is undefined. So the slope of this guy, we'll just say undefined. Okay? But if you're still not sure of that, just pick any 2 points. So if I pick this point, okay, this would be 3, 3. And if I pick this point up here, this would be 3, 6. Okay? So if I just go ahead and subtract them, so we're going to have 3 minus 6 over 3 minus 3. Well, already you can see that the bottom is a 0, which we know is undefined. So I think you kind of have an out. A lot of times times in mathematics, it's nice not to memorize things. If you have a process where you can confirm an answer, do it. But with slopes, that's really not a hard thing to do. Okay. Moving on. Given a line with slope m and y-intercept of 0b, the slope intercept form of the line is given by y equals mx plus b. Okay? Which is drilled into your head as soon as you start learning how to graph points. When you first learn the coordinate plane, right? What's positive, what's negative? Your teacher's like, okay, let's graph. And this is the first thing they said, you know? And it works, you know, this is what we use to graph. So m is gonna be our slope value, and then b is our y-intercept, which 0b, just to write it as a point there, okay? All right, so let's use it. Given the following, we're going to first write the equation in slope-intercept form, then determine the slope and y-intercept, and then the last one, graph the line by using the slope and y-intercept. Again, we've done this already. So, nothing too exciting right now, and that's fine. I think every once in a while it's nice to have a lesson that's kind of easy just to relax, listen to. So let's see, slope-intercept form, that's this guy. So I gotta rearrange it. Well, to do that, I'll add 2x over. So 8y equals 2x plus 16, and then divide by 8. So that'd be a fourth x plus 2. There we go. Okay, next, slope. It's in front of the x value, the coefficient, that's a fourth. And then y-intercept is gonna be 0, 2. And please make sure when you write this, write it as an actual intercept point. Don't just put 2 as an answer. And then last step, graph the line. Sure, why not? I think 5 would be good. 1, 2, 3, 4, 5. And typically when you graph these, the easiest thing to do is just graph the y-intercept first as your initial point. So 0, 2, there it is. Use the slope to graph additional points. I'm only gonna graph one more point. I think that's good enough. So up 1 to the right 4, and then, cool. Okay, so there's my line. Again, if you wanna continue further, you can graph additional points for accuracy. What we could do is we could take this guy, and the last lesson we talked about functions, right? So we could take this and now flip it to some function notation, right? Let's do that next. So let's let m and b represent real numbers where m is not 0. Then we have this. Function defined by f of x equals mx plus b is a linear function. The graph of a linear function is a slanted line. Okay? So I'm taking y out, I'm putting f of x in its place. That's the only change. Let's highlight it. Okay, so here it is. So I'm taking y out and just swapping it for f of x. We've already talked about what that means anyway. So nothing new. Next, a function defined by f of x equals b is a constant function. Okay? So no slope, no slope whatsoever. The graph of a constant function is a horizontal line. So a good example is the one over there. There's our horizontal line. So this guy would be a constant function. Okay? This would not be a function, so we have no name for that one there. All right. Let's use it. Now that we have that defined for us, let's try an example. Write the equation of a line that passes through the point -1, 7, has a slope of -2. Then write a linear equation using function notation where y equals f of x. Okay. So we have the slope, we have a point that it passes through. Can we create the equation, and then afterwards, can we write function notation? So essentially, we're gonna make this, and then our last step is to swap f out, put f of x in. We're good to go. Okay. So, good first step, list your givens. Why not? So we know the slope's -2, that's what m is gonna represent for us. And we know the point. Okay. So, what do? You could graph this. Plot the point, use the slope, and see where it hits the y-axis. Never fails, you could do that. However, what if it crosses the y-axis at, like, in between 2 points, right? That's where it gets kind of tricky. So we have to have an algebraic way of finding that y-intercept. Then we can create our line. So if this works on my line, and this is my slope, what I can do is take the slope-intercept form, as it is, and I can plug these numbers in and solve for b, okay? Because again, these numbers are on that line. So b is, it's kind of forcing b to work with this stuff, which is gonna be our y-intercept. So this is my x and y coordinate. I'm gonna plug them into here along with m. Bless you. So we get 7 equals -2 times -1 plus b. Now, I don't know if this is kind of clicking your head like, wait a minute, there's another way we can do this. We'll talk about the slope-intercept form, point slope form in the next lesson. But this, we're just gonna use this way. So 7 equals 2 plus b, so b is 5. So in other words, 0, 5 is my y-intercept then. So my equation would be y equals -2x plus 5. And then with function notation, it'll just be f of x equals negative 2x plus 5. There we go. Okay. All right, I think we're on computing average rate of change. Let's look at that one now. This just kind of sets the groundwork for it. Okay, let's say I had something that looks like this. Trying to write sideways is quite tricky. Okay. So let's say I had a basketball and I dropped it, okay? And I want to measure how far it takes to get to the ground, okay, how much time it takes. So I have all these points to keep track of its progress, okay? So something like this. And again, this is just a rough graph. Okay, let's say those are the times, that's the trajectory. And I'm going to go ahead and just, can I connect all the dots at once? Oh, no, I can't. That's all right. We got as close as possible. Again, I'm not doing anything accuracy-wise. I'm just drawing generic graphs. So there's the height, there's the time for a basketball just being tossed, okay? So one of the things we have to take into consideration is that not all graphs, shocker, right, are linear. Okay, so obviously this graph doesn't represent a linear function. Well, that's due to talking about gravity and so forth, but that's okay. We could still use this graph to still calculate other things as well. So, however, we can use what's called linear approximations to analyze nonlinear functions on small intervals. Okay? So that's the key. We could still make analysis with this. We could still analyze things, but we take smaller intervals. Okay? So if you like to highlight or color or whatever, this would be a good opportunity. Okay? So I'll show you what I can do. So I can take maybe this interval. Okay, maybe it intersects the graph at these 2 points. So I'm going to analyze that interval with that line. Okay, and talk about what changes do I see between those two. I can go a different direction. Okay, I can have another line that intersects over here with these 2 points. And let's say I want to know the changes that are happening from here to here. That's a larger chunk of time, right? A larger interval, which could get messy. The larger the intervals, the more prone that your answers and analysis might not be correct, okay? So these lines that I'm drawing, notice that they're hitting the graph at 2 points, okay? So a refresher from geometry. A line drawn through 2 points on a curve is called a secant line. Does that sound familiar? From geometry, secant line?
Chord, but that's a
Oh,
segment.
chord. Chord would be a segment in a circle, yeah. It intersects at 2 spots, but not through the center. This is a little different. So yeah, secant line where it's just touching the curve at 2 spots. Okay, so that's what we're doing. We're going to be creating these secant lines and analyzing just what's happening in terms of changes on that interval. Okay? All right, now that we have a visual and a little bit of the idea of what we're doing, let's put it to a definition here. Okay. suppose that the points x1, y1 and x2, y2 are points on the graph of a function f. Using function notation, okay, these points are x, f of x1, and x2, f of x2. Okay, so I took, I'll highlight. I love this blue, it's a nice color. So I'm taking y1 and y2 out, and I'm using function notation again. So this is where the f of x stuff comes in. They're still representing the coordinates. This is just saying, hey, you plugged x1 into the function and you spit out an output value, okay? Now that we have these guys established, let's talk about average rate of change with these symbols. So if f is defined on the interval x1, x2, then the average rate of change, I'm going to underline that, on function f on the interval x1 and x2 is the slope of the secant line containing x1 f of x1 and x2 f of x2. Okay, so if f is defined on this interval, which is what I drew over there in the graph, like pick 2 points, what 2 x values are we talking about, then the average rate of change on that interval is the slope of that secant line. Okay, so that's what we're doing. So let's write the formula down. So the average rate of change is the following. Okay, so it's still, again, it's the slope, right? Which we know this is what slope is. But what I'm doing is I'm taking out these guys and I'm rewriting them with function notation. Okay, so that's the big change for us, is getting us used to seeing this. Because I will tell you that from here on out, you're not going to see me write y2 minus y1 as often anymore. I'm going to write them more with functions. Obviously, if the graph or the equation is a function, I'm going to use that notation. Okay? All right. So let's give it a shot. Let's do some calculations here. I'm going to leave that graph up too, as a visual. Okay. So let's talk about that basketball again. Using the prior example, which is this guy, what I did for you guys is I just took a snippet of the XY table, okay? So again, I wasn't going to be too accurate with the graph because we just need a general graph just to analyze the concept. but here's a table that shows the time. So at 0 seconds, the height of the basketball is 5.23594. After 0.08 seconds and 0.179988 seconds, these are the heights right here, okay? We have a really good camera to see all this stuff, so we know exactly where we're stopping here. So the first thing we're gonna do is we're gonna find, so it says here determine the average rate of change. Okay. So part A is from t equals 0 to t equals 0.08 seconds. Okay. And then part B, we'll put underneath it, we're gonna go from 0.08 seconds to 0.179988 seconds. Okay? And we'll make some comparisons. So in other words, I'm kinda, well, I guess this could have been it. I think it's a little too far out, but it'd be like something like this. We're comparing this secant line slope with another secant line slope. And then we're gonna analyze at the very end, like what does that mean? And that's honestly critically important. I mean, you guys know how to find slope of a line, that's obvious. But to interpret it, that's the key thing, right? Knowing what it means. Because especially when you get to calculus, you're gonna do a lot of slopes, okay? A little bit more in detail, obviously, but slopes are very important in calculus. Okay, so for this one, average rate of change. Actually, you know what, I'll put that beneath. I think that's not gonna give me enough space. I'll put this underneath here. Okay, so average rate of change. I'll try and abbreviate. So we're gonna take, if you look at the formula, I'm gonna take the second point minus the first point. Okay, so this would be my second, this would be my first. So I'm gonna use the symbols to represent it, so that we're used to seeing it. Okay, so f of 0.08 minus f of 0 divided by 0.08 minus 0. Okay, so that's gonna be the following. If I can write things correctly, geez. Okay, so I just plugged the y values from the chart. That's all I did for the next step. Just a little substitution. And I'm gonna be out of space, but we're gonna still try and fit it in here. So we get negative 2.610875. Okay? And then for part B, I'll put underneath here, so average rate of change. So f of this lovely number. Bless you. Okay, so I'm taking the second point, which is this guy, and subtracting it from the first point. So this is the y's that I'm subtracting, and these are the x's. So my next step is I'm gonna plug these out and put in the y values that correspond with it. So I'll highlight this because it might get a little messy with them put together. Okay, so there's me just substituting those values for us. Okay, and to finish, that'll be negative 5.258131. And I'll highlight that as well so we can go with that. All right. So, what's that mean, right? I guess I gotta get rid of the graph, huh? That's sad. Such a beautiful graph. Oh well. Okay, so this means the speed of the basketball increased 2.61 feet per second during the first 0.08 seconds. Okay, so that's what the first one's telling me there. So from 0 to 0.08, the average speed increased by this much. Okay, let's continue. The speed of the basketball increased by an average, and that's the key thing here. These are averages, okay? We're not talking about instantaneous speed. That's more of a calculus thing. We talk about like limits and how that leads you to derivatives. But for right now in this class for college algebra, we're just talking about the average changes of speed. So by an average of 5.26 feet per second during the next 0.099988 seconds. Okay? So right now we just have the capability of finding averages through each interval just to see what's happening there. Now you're probably guessing like, well, there's negatives. Do we just ignore the negatives? No. The negatives are indicating that the ball is falling, right? Okay, it's telling you the direction of the projectile, the direction of the basketball itself. So the negative is just indicating that, okay? It's not just me ignoring it. If it was positive, I'd be worried, because if I drop a basketball from my hand and it does this, I shouldn't be standing on the ground then, huh? I would also be going upwards, because gravity is not doing what it should be doing. All right. So last thing we're gonna do on the list is solving equations and inequalities graphically. So let's go ahead and do that. I only have one example with that, that's not too bad. So a quick recall, if we have two linear functions equal to each other, then we want to find an x value that satisfies the equation. Graphically, it will be where both lines intersect. Okay, so that's when y1 equals y2. Okay, so you have two linear functions that are equal to each other. That corresponds to the graphs colliding with each other. So here we go. Last example. Solve the equations and inequalities graphically. Okay, so we got three situations here. It's the same equations for each one. This one just has an equal symbol, this has a less than, this has a greater than symbol. And why not? I've been highlighting things, we'll just keep highlighting. Only because I really like the color, so we'll keep highlighting. Okay, so here's the graph that we're looking at. Just so you guys get a gist of it, I'm doing 8 grid lines. Okay, so I counted everything to 8 there. So I'll write the points out so that way you can graph it a little bit better in your notes. Okay, so there we go. So there's the points. Why not? Let's use some colors. Let's make it pretty. Okay. I'm gonna have to block just for real quick, guys. There we go. Can't forget the arrows. Gotta be proper. Perfect. Okay. Oops. Alrighty. So now we just gotta answer the questions. And with the graph, it's, well, relatively simple when it comes to this, okay? So taking a look, and I apologize, I guess it is kind of hard to see that point. Let me rewrite that underneath it for you. So this point right here is -4, -1. There you go. So the first one, part A, says, hey, where are they equal? Where are they equal to each other? Well, that's where they hit each other. Right here, they're equal at this spot. So what's the x-coordinate at this spot? -1. So my solution set for A is -1. We're done. That was easy. Okay. Next. Part B. When is this line less than the other guy? Okay. And let me, since I use colors, my apologies. I should put the colors underneath it so you know what line's what. Probably, I mean, honestly, you probably can gather which one's which, but still, make it a little bit easier here. So this would be y1. So we'll say that's y1, and then this guy's y2. So there's y2. Okay, so let's just put that up here. So this is y1. This is y2. There we go. Hopefully that helps. That way it's a little easier to make the comparison. So for what x values, and there's more than one x value that gives us this, is this guy, y1, less than the other guy? Okay. All right, that doesn't seem too hard. So looking at this, at -1, anything less than that, we could see that this pink line, y value-wise, is larger than this guy. But if I go past -1, okay, I can see that y1 is a lot less than y2. And when I say less, I'm talking about y values. So these y values are negative, y2 values are positive. So from -1 onward, this is when this case happens. So for this solution set, I got too many markers in my hand. It's going to be anywhere from -1 to infinity. Okay? Not including -1 because again, it has to be less than it, not equal to it. Okay, and then the last one. When is y1 larger than y2? Okay, well I kind of mentioned it already. That's this case, right? When you go less than -1, this chunk of the graph is larger than that chunk of the graph, okay? So essentially I'm just flipping this guy. So from -infinity up to -1, but again, I'm not including -1, that is when that inequality is a true statement. So I mean, for me, can you figure this out with an XY table? Absolutely. It's not a bad thing to do. But I think just graphing it real quickly, you can kind of see visually like, okay, when are these less than or greater than each other or equal to each other? Okay. All right. Any questions? Guys are golden.